Okay, so hi everyone. Let's begin with some of the basic preliminaries about functions and growth of functions that is important for this class. So the first thing that we would like to know here is about big O and big omega notations. These are notations that we will use to sort of simplify some of the calculations that we will require to do in this course. So what is this? So this is going to appear more or less when we try to discuss runtimes of algorithms. So the runtime of an algorithm will usually be considered as a function of the input, and it is there when we try to compute the growth of the runtime that these notations will appear. So let me jump to the definition right away. And let us just begin with functions which give us positive integer values. That is just because it makes things much nicer. So let f and g be two functions which go from positive integers to, let's say, positive reals. Okay, z plus to r plus. We will extend this definition a little bit more, but there is really no difference. I mean, finally, for most cases, it's actually of this kind, functions which go from positive integers to positive reals. Okay, so let f and g be functions from positive integers to positive reals, and we have two definitions. Okay, so this is about the growth of functions. So the first one is that we say f is equal to big O, it's called big O, and it's written just as an O. Okay, big O of g. If, what does this mean? So if there exists an n naught, positive integer n naught, or let's just rewind a bit. There exists a real number c positive and an n naught, such that what should happen? Well, f of n should be at most c times g of n for all n greater than or equal to n. What does this mean? What this means is for all n greater than or equal to n naught. That means after a certain point, for every input n, the function value of f at the input n is bounded above by the function value of g at input n up to a constant. It's not necessarily fn less than or equal to gn, but fn less than or equal to a constant times gn. Okay, and actually we will come across many occasions where f is a simple function and it can be bounded above by a simple function g, but up to a constant. A constant will appear, and we don't really want to keep writing this constant in our calculations. That is why we hook up this simple notation called big O, so that we don't have to keep writing the constant. Okay, so when you write big O, it means there exists a constant such that this is true. We don't really care about what that constant is after that. Okay, there is some constant, that's all, and that is enough for us. Okay, so that is what this is, and omega is of a similar kind. So what does that mean? We say f is omega g. So let me just write it a little more neatly. Omega g, if once again there is a constant and an n naught, such that f of n is in fact greater than or equal to the constant times g of n for all n greater than or equal to n. What does this mean? Meaning is quite similar. So what this means is after a point n naught, which means eventually for all large inputs n, the function value f of n is in fact bounded below by g, right? Greater than or equal to. So we have bounded below by g, but up to a constant, not exactly by g of n, but up to a constant, right? And we want to hide this constant in computations because it's an inconvenience when the computations become more and more difficult. So in order to hide that constant, we use this simpler notation omega. Okay. And the next important thing is once we have this notation, we will actually sort of relax our notation. So notation, we can also write these as f of n is big O g of n, or f of n is big omega g of n. Okay, because sometimes it might be easier to write the expression for f in terms of n rather than writing f. Okay, and therefore we will relax our notation and say f of n is big O g of n, f of n is big omega g of n, however it comes there. All right, is that fine? This is the definition. Just when you listen to this, you should probably, we'll go to some examples now, but when you go to examples, you should come back and look at this definition once again to convince yourself that this is fine. Okay, so let us look at some examples now. Let's look at some very, very simple examples. So now I will use the notation that I said. We'll write it as fngn instead of fng. So examples. All right, some very simple examples. Let's do. So one is in fact big O n, the function one all the time. For every input, the output is one, constant function. This is in fact big O n, right? Why is that? Well, let's give a small proof. Okay, so let's go back to the definition. What is it? If we have to prove that f is big O of g, then we need a constant, and n naught says that for all n greater than equal, for all n greater than or equal to n naught, this is true. All right. But if you see here, 1 is in fact always less than or equal to just n itself. The constant now is 1 for all n greater than or equal to 1, right? For all n positive. So n naught here is just 1 itself. Constant is also 1. The constant here, in fact, is just 1. Okay. So this is a trivial example. Okay. So trivial example, 1 less than or equal to n for all n. Therefore, 1 is big O n. All right. Do you see, this is in fact a very, very simple example because 1 is also big O square root. Why is that? This is because, once again, for all n greater than or equal to 1, we have, so n is greater than or equal to 1 implies square root n is greater than or equal to 1, right? So square root n is in fact greater than or equal to 1. Note that when you write square root, you are actually by default meaning the positive square root. There are two square roots minus, but negative square root we will specify it using minus notation. Okay. When you simply write square root, it means positive square root. So square root n is greater than or equal to 1, or in other words, 1 is less than or equal to square root n. Okay. and therefore 1 is big O square root n. Okay. Third, let's look at these itself. Let's consider slightly more complicated functions. Let me say square root n is in fact big O n. Do you see why? Can we give a small proof? So since we are only considering positive numbers greater than or equal to 1, we have, what do we have? Square root n is in fact less than or equal to n. This is not true actually when the number is less than 1. Okay, but since we have n greater than or equal to 1, we square root n is in fact definitely less than or equal to n, and therefore once again the constant is 1, and we have this for all n greater than or equal to 1. So square root n is less than or equal to n, and therefore square root n is big O. Okay, fourth one. Now let us see. Is n big O of square root n? What is the guess? So the answer in this case is no. Why is that? Because now we need to give a slightly more involved argument. We need to give carefully written proof. Okay, so let me go to the next slide and let's show this. So the question once again is n equal to big O square root n, and the answer is no. Okay, so what is it? So how to prove this? So answer. How do you show this? Well, the inequality goes the other way around. That's one way of looking at it. So it should not be very difficult. But a technical proof, one has to be a little more careful. Okay. So what do we need? We need an n naught and a constant such that this is true. If we have to show that n is big O square root n. But that's not going to be the case actually, because n is going to be larger and larger than square root n. So bounding it by a constant is not expected to be true. So let's prove by contradiction. Okay. Suppose n is in fact big O square root n. Okay, so let me be more careful so that things are, since this is the first class, let me be a little more careful. So we prove by contradiction. Okay, suppose n is big O square root n. What does this mean? This implies, by definition, there is a constant c greater than 0 and a positive integer n now, such that n is less than or equal to c times square root n for all n greater than or equal to n naught. Is that all right? That should be fine then. Okay. But then there's a problem, right? For all n greater than or equal to n naught, this is true. So n naught is positive. So all these n and square root n, these quantities are all positive numbers. So we can always divide and the inequality remains the same. So this implies square root n, which is n by um, n by square root n. If I divide this is less than or equal to constant c for all n greater than or equal to n. But n by square root n is square root n. So this plus square root n is less than or equal to c for all n greater than or equal to n naught. At this point, we have a trouble. Do you see why? The problem is that, well, n is greater than or equal to n naught, and this is true for all n. So you can take n as large as you want. But C is a fixed number. C is a fixed positive number, right? There exists, that's what we have said. There exists a C which is fixed positive. You cannot change it now. It's only one choice. And for this choice of C, everything goes through. Correct? But then that's not correct, right? Because it's like saying n is less than or equal to, or square root n is less than or equal to 5 for all n greater than or equal to 10. That's not going to be true. So now how do you contradict this? Well, you just pick a constant for, you just pick a choice of n for which this is not going to be true. So since we have square root, in order to make this an integer, we can choose n to be some square of some number. So in particular, so this implies for n equal to, so let me make a choice. N equal to, I don't know what n naught is, so I have to be a little more careful. Okay, so let me do a small rough work because before I write down the final. Okay, so the rough work here is, if I choose n equal to c plus 1 squared, then this will give me square root n equal to c plus 1. And that is not less than or equal to 0. That's a contradiction. But this is not enough actually, because whereas there is an issue of this n naught, I have to accommodate this n naught. Now n naught could be much larger than c plus 1 squared, or so then I cannot contradict this with just that much. However, if this is contradicting for c plus 1 squared, then this is actually contradicting for all choices greater than c plus 1 squared. So rough work aside, the small adjustment that one needs to do is just then take n equal to, what should I do? I'll just accommodate this. So max out of n naught plus 1 and c plus 1 squared. So n is definitely greater than or equal to n naught, and all of this is true. Right? What does maximum mean? This implies n is definitely greater than n naught, because greater than or equal to n naught plus 1, greater than n naught, and n is greater than or equal to c plus 1 squared. We have both of these. This implies for this choice of n, so let's call this n prime, because let's just be a little more careful. N prime. This implies square root n prime is greater than or equal to square root c plus 1 whole squared. Why is that? Because n prime is greater than or equal to c plus 1 squared. That is equal to c plus 1. So this is what we get from just this statement, right? But now if I call this to be star, by star, since n prime is greater than n naught, what do we get? We get square root n prime less than or equal to c, which is less than c plus 1. And that is my contradiction. Proof by contradiction. Okay. So what does this mean? If you suppose that this is true, then you're getting something that is a contradiction. Okay. On one hand, you prove that square root n prime is greater than or equal to c plus 1. On the other hand, you show that this is like less than c plus 1. That is a contradiction. So to finish this off, and the end, what are you supposed to write? So we have a contradiction. Thus, what we assumed was wrong. So what did we assume? N is big O square root. N is not big O square root n. Okay, that is what this is. Fairly simple. Now let's go to some examples of omega. Omega actually is slightly easier. Okay. So how do we look at this? Well, first example is quite similar to what we saw. N is in fact big omega 1. Why is that? Once again, you need a constant C and an N naught. Well, but we have N greater than or equal to, this is the proof. N greater than or equal to 1 for all N greater than or equal to 1, right? And quite easy. So that is why this is true. Second, even square root N is omega 1. Why is that? Since N is greater than or equal to 1, we have square root N greater than or equal to 1 for all N, and therefore this is true. Right? Third, similar thing. N is in fact big omega square root. And why is this true? Well, once again, for all N greater than or equal to 1, we have N greater than or equal to square root N. And therefore this is true. Constant is this. Constant is 1. Okay. Once again, what do you think now? Is square root N equal to omega N? So now compare this with what you did in the big O case. And this is the first exercise. Okay, I would expect someone to solve this during the tutorial, or at least tell me what they were trying to do during the tutorial. Okay, is this true? Yes or no? Okay, the answer is no, but just have a look at it. All right. So that is it. And what is the relationship between big O and big omega? There's a very, very simple relationship. So this is the theorem. So once again, let's say let f and g be functions from z plus to r plus. Okay. Then, so let me write it in the notation that we have started using. F of n is equal to big O g of n if and only if I hope everybody is familiar with this if and only if notation. Okay, if and only if g of n is big omega f of n. Okay, so big O and big omega are in some sense inverse relations. F of n big O g of n if and only if g of n is big omega f of n. How do we prove this? It's an easy proof. So let me just quickly show this. Suppose, so what does it mean if and only if? You have to assume one side and prove the other side, and you have to do it the opposite way as well. Right? So let's go one side. Let us show LHS implies RHS. So suppose f of n is big O g of n, right? Therefore, by definition, what does this mean? This implies that by definition there is a constant c greater than 0 and n not positive, such that f of n is less than or equal to c times g of n, for all n greater than or equal to n naught. This is the definition. Now note that C is a positive number, so I can always divide by C and the inequality will not change. So this in fact implies 1 by C times f of n is less than or equal to g of n for all n greater than or equal to n naught. But that is exactly the same as saying g of n is greater than or equal to 1 by c times f of n for all n greater than or equal to n. But c is a positive number, so 1 by c is also a positive number, right? So if we take c prime to be 1 by c, this is again a positive number. So for this choice of positive number c prime, then we have g of n is greater than or equal to c prime times f of n for all n greater than or equal to n, right? And now this is now by definition, this is actually, this implies g of n is big omega f of n. Just check by definition. Okay, that is what this is. So if fn is big omega big O gn, then gn is big omega fn. Conversely, let's do the other way around. Conversely, suppose what do we have to show? G of n is big omega f of n, right? Now I want all of you to again follow this definition and go all the way down. So, and prove this and finally conclude that f of n is in fact big O g of n. Okay, this argument is very similar to what we just did in the previous slide. So this is again an exercise. Okay, try doing this. Try writing it down. All right. We will discuss all of this once again in the discussion session, but there it will be more of doubt solving. Okay. So have a look at what we did so far. Think about it, and the two exercises that we just had a look at. Try it before we meet the next time. Okay. So that's it for the moment, and we'll meet next time. Thanks.